All right, in this video we're going to look at rotational dynamics. And it starts with trying to figure out how easy or difficult it is to rotate a specific object. And how can you change that? So we did a demo in class. And if we didn't do the demo, if you're watching this without having seen it, we had two sticks, red stick and blue stick, and they were both the same size. So they had the same mass. Overall, they had the same length, same shape, same radius. And when we rotate them both back and forth and have a race, one of them was really hard, and one of them was really easy, even though they had the same dimensions and mass. And what we saw was, it's not just the overall mass that's important, but it's how that mass is distributed. And the one that was really hard had more mass further away from the center. So the hard one, I don't remember which was which, but the hard one had most of the mass distributed far away from the axis, so it was really hard to swing that back and forth as you rotated it like this way, like back and forth, back and forth. And the one that was easy was the opposite. It had most of its mass distributed close to the center. So this one you could go back and forth, back and forth, back and forth very quickly. So the mass was closer to the center. The way we would really quantify this is in terms of the R value of the mass. So the R would be the position at which the mass is distributed relative to the rotation point. And in this example, the shorter the R, the easier it is to rotate. The higher the R, the harder it is to rotate. So we have a specific name for this quantity. It's called the moment of inertia of an object. It's denoted as capital I. And in one of the videos you're going to watch, we will derive for you this expression. But really what I is the sum of all the little mr squareds of the mass distributed about an object at some position r away from the point of rotation. So as you can see, as r increases, r gets bigger, the moment of inertia increases, right? As these go up, they're directly related. Or actually, I is directly related to the square of that radius. So we call this the moment of inertia of an object. Now note, different objects can have different moment of inertias based upon their orientation. So you don't have to memorize how to calculate moment of inertias. You will typically be given the size or the shape of an object, or the size and shape of an object, and you'll have to figure out how to find I off of some table or some given quantity. So what I'll post is a chart like this, and what you can see here, I'll zoom in a little bit, it's kind of hard to read, is that different mass distributions will have different moment of inertias depending upon how their mass is distributed. So a thin hoop, radius r, through the center, so this is rotating at about the center, its moment of inertia will be the mass of the hoop times r squared. All the mass is distributed at the same r. But if you take that hoop and you put it up on its end and rotate it vertically about its axis, its moment of inertia becomes 1/2 mr squared plus 1/12 mw squared, where that's the width of the hoop. So notice, if you change the orientation in which you're rotating the object, the moment of inertia changes. Same thing with a solid cylinder. This one we'll use a lot, like a disc. If you rotate about its center of mass, its moment of inertia is 1/2 mr squared. But let's say I were to fix it on one end and then rotate it about that end, I would have more mass distributed at a higher r, and then I is going to increase. So when you're doing rotational dynamics problems, pay attention to what the shape is. Use a chart to look up the moment of inertia for that shape. Again, you won't have to memorize those, but pay close attention to how it's oriented as well, because you can have different shapes oriented differently and come up with different results. Okay? So now what if I have an object that is free to rotate when I apply some net torque? So at what point will it tend to rotate? So really two ways to look at this. In this first example, we have a wrench where we have a known center of mass, and that center of mass is closer to the heavy end than it is to the lighter end. And if I were to just spin that wrench, give it a torque while I fired it through the air, what we would see is a couple things. One is that as the wrench rotated, it would rotate about that center of mass. So if I have an object free to rotate, where it is not fixed, that object will tend to rotate about its center of mass. Now notice another thing, if I track the center of mass, because it's rotating about that, the center of mass will track through the air like a point particle, kind of like we dealt with, like for example in this projectile problem. If we track the center of mass of the wrench as it goes through, it would track just like a projectile would track without rotating at all. So another example here is a diver. When a diver jumps up, what they do is they collapse into a ball. When they collapse into a ball, they've decreased their distribution of mass. All their little mr squareds, these r's goes down, so all the mass is distributed closer to the point of rotation. That makes it easier for them to rotate. And then when they're about to enter the pool, they want to slow down that rotation. So then they extend their arms and legs out, and what they're doing is increasing their r, and that increase in r decreases their I. And really this property will be called conservation of angular momentum. That's the way we're going to be able to quantify it, why the I decreases. It's based on this conservation principle. But you can just see lower r, you'll always rotate about the center of mass, but as you change your mass distribution, you're going to change the rate of rotation based on changing I. Now, we have other type of problems with rotational dynamics, not those where it's free to rotate without a fixed point, but objects where you have a fixed axis given, and then they're forced to rotate about that axis. A classic example of these are door problems. Like we have a door that's hinged, say, at some wall here, and the door is attached to that hinge. Now the center of mass of the door is through the center of the door. So, but there's a fixed axis here, and that's the hinge. And so we're forcing the door to rotate back and forth about this fixed axis. So we would treat this door as an object. It would be like a rectangular prism that's rotating about its one end, not rotating about its center. If you can imagine, a door would be a lot easier to rotate about its center because if you rotate it back and forth like this, there's lower R values for all the mass. When you rotate it about a hinge, you have this chunk that's way farther away, and so you're going to increase the moment of inertia of a door if you rotate about its end. The difference is, why don't we rotate doors about the center? It's easier, but notice when we rotate it, we only have half the distance to go through. And so we've chosen to rotate them around their ends, even though it's harder to give us a wider opening. Okay, a couple more things, and then we'll wrap this up. What happens when we apply a non-zero net torque to an object? So let's try to quantify all of this. And we have the rotatotron. And we did this with the rotational kinematics lab. And when we had the rotatotron and we wound up a cord and then we dropped a mass on it, what that mass did was exert a torque at some lever arm R with some downward force F, and that torque, F dot R, caused the rotatotron to accelerate. And we gave a name for this. The rotational acceleration, rotating at a higher rate, became our angular acceleration, which we denoted alpha. And the standard units of alpha were radians per second squared. And so as long as the torque was constantly applied, we would have a constant angular acceleration alpha. Now, how do we relate this to linear dynamics and to Newton's second law? Well, what we saw in first semester was that a net force caused a mass to accelerate. And this would be translating through space, either left, right, up, and down, in whatever direction it's moving. But forces applied to masses cause accelerations. Now, if we start to look at this from an angular point of view, we have a similar structure in that now a net torque, which is the sum of all the F perpendicular times R's, about some point of rotation, will cause an angular acceleration alpha. Now, what is that going to be based on? Well, the equivalent to mass in terms of rotation is the quantity we just spoke about, and that is the moment of inertia, or how difficult it is to rotate the object. So when we're applying Newton's second law for rotation, we see that a net torque about some object's point of rotation will be equal to its moment of inertia about that point of rotation times the angular acceleration alpha. So in all the problems that we're looking at, we're going to need to know the shape and mass distribution to determine alpha, or determine I, excuse me. But then, just like we did in first semester, we're going to sum all the torques acting on that object, and based upon proportion here, that net torque will be equal to I alpha, where alpha is in radians per second squared. And that's the basic fundamentals of rotational dynamics. In the problem-solving process, we're going to follow similar to what we did before. We're just going to look at it from a rotational point of view.